Hello everyone and welcome back to this video. Did you finish your finite element analysis and ANSYS tell you that the stress in your bolt is only 180 megapascal, for example? What if I told you that your bolt are already carrying several hundred megapascal of stress before you even apply the external load? So if you ignore that stress, your safety assessment could be completely wrong. So in this video, I will show you how to calculate the stresses introduced during bolt tightening according to VDI 2230 guideline, which is like ANSYS don't show to you. The same approach as actually like used in professional bolted joint design. For that, we are gonna use this table. I already prepared for you a table to calculate the torsional stress, which is like come out like from the tightening of the bolt. So in the previous video, we built this like bolt plate connection in ANSYS using 4 M8 bolt with a strength class of 8.8. We then like applied like an upward load of 20 kilonewton. Actually, I did this like in this case, 20 kilonewton on the middle upward, and obtained the stresses in the bolt from the finite element analysis. So if I go to equivalent stress there, we can see actually the stresses on the bolts. The step 1 or time 1 is actually when we like we don't have already like the external load, we have just bolt pretension. We had like stresses of about like between 507 to 512 megapascal on this bolt just coming from the preload pretension. However, there is like one important piece missing. So ANSYS only give us the stresses resulting from the external load, which we can see like on the second time or step 2, which is like 580 megapascal. And in reality, like every bolt is already highly stressed because of the tightening process. So before we can determine the true stress acting on the bolt, we first need to calculate this assembly stress. That's exactly what we will do in this video. So when we tighten a bolt, we don't simply clamp two plates together, as you can see. Actually, like the bolt is stretched like a spring, as you know, and creating a preload that holds that joint together. So at the same time, the bolt experiences torsion because of the applied tightening torque. So during assembly, the bolt is subjected to two different stresses: axial tensile stress caused by the preload itself, and a torsional shear stress caused by the tightening torque. According to VDI 2230, both stresses must be considered because together they determine the equivalent stress inside the bolt during tightening. I have already, like as I told you before, prepared like this calculation table, and we will go through it step by step by the end of this video, so you will understand exactly where every number comes from and how the assembly stress is calculated. So actually we begin with the bolt geometry and material properties. So in our model, we are using M8 bolts with a property class of 8.8. The table contains actually all the required dimensions such as the stress area, thread diameter, pitch, and like proof strengths. It's actually in this table not like required, but in order to get the safety factor we need it for sure. So these values are either like taken directly from the ISO standards or calculated according to VDI 2230. So the next step is determining the assembly preload, and this is the force generated when the bolt is tightened actually. Depending on the tightening method and the required clamp force, VDI 2230 defines the minimum target and maximum assembly preload. In our case, we will use the maximum preload because it's like produces the high stress inside the bolt and therefore represent the critical condition during assembly. As you know, I already like post a video before it, like which is like show like what bolt pretension to each like bolt size and strength of class. You can like see this video in details, like I explain like how to get these values, and I already share a table that show all these information. You can like watch it. In our like case, on when the preload like is known, as you can know, I will like make it like visible in our case, which is here actually. So for our M8 bolt with a strength class of 8.8, they have like a bolt, or they must like with a bolt pretension of about like 18.6 kilonewton or 18,600 newton. And once the preload is known, so calculating the axial stress is straightforward, which is actually the preload pretensions divided by the stress area of our bolt, which is like 36.61. And dividing this force by this area, we get the following axial stress from the preload, which is like about 508 megapascal. Comparing this value to the value like coming out of from our FE analysis, so I'm going back to our analysis there, and I will show that table again. As you can see in step 1, when we have like only like the bolt pretension, we have like actually around like 508 megapascal, which is like aligned with our analytical calculation here. So we simply like divide the preload by the tensile stress area of the bolt, and this gives us like the tensile stress caused purely by stretching the bolt, which is like from the bolt pretension. Now let's calculate the thread torque, which is like come from the tightening. So next we calculate the thread torque, not all of the tightening torque like it twists the bolt, part of it like it lost under the bolt head because of a friction. So while the remaining part act like through thread and generates torsional stress. Using the thread geometry and the friction coefficient, we calculate the thread torque according to VDI 2230. So now we calculate the torsional shear stress. In order to do that, actually, what we need is the coefficient of friction, which is like could be variable. In my case here, I took like a frictional coefficient in the thread and overall actually also under the bolt head and between the two plates of 0.12. Like this is what I already defined also in my model behind this screen. So we have 0.12 as a frictional coefficient. Now the geometric like parameters, which is like relevant to each bolt size, you can find it as I told you before from the standards or like VDI tables. So for our M8 bolt, we have a pitch of thread of 1.25, and we have a pitch diameter, which is called also D2, of 7.188 millimeter. And we have the minor diameter D3, which is like in our case here 6.466 millimeter. These values are like required in order to calculate the next parameter, which is we will be talk in a bit like about in order to calculate finally the maximum torsional stress acting on the bolt, which is coming from the tightening of the bolt. So as you can see to the right, I already like put to you like the formulas, which is like used also in this table automatically. So all what you have to do actually is to input this, which is like in the blue colored right now, and you will get directly the maximum torsional stress. It's like based on these formulas. So what we need actually to calculate the maximum torsional stress is to know the tightening torque divided by the polar moment of resistance of the bolt cross section. First of all, in order to calculate the torque thread, we need to know the bolt pretension, which is we already know, and we already like took this value from the table from VDI. As I told you, you can like see the previous video, like to know the bolt pretension for this bolt or for any other like bolts. I already like shared this information before, and this will be multiplied by the parameter D2 divided by 2, and all of them like multiplied by the pitch over pi multiplied by d2 plus like 1.1155 multiplied by the frictional coefficient on the thread. All these parameters are already known for us, so based on these calculations I get the thread torque of about 12,966 Newton millimeter. This is like one of the two like most important parameters in order to calculate our torsional stress. So this is like already like calculated. Now the second parameter, it's the polar moment of resistance, and it has like the following formula, or in order to calculate it, it's like just pi divided by 16 multiplied by a parameter called ds power 3. So if you already have ds from the standard, so you can use it directly. In my case, it was like unknown. ds is actually not more like than the average between d2, which is we have there, and the d3. So it's like d2 plus d3 over 2 power 3, and you will get actually finally the polar moment of resistance. And in my case here, it was like about 62.48 millimeter cube. Now, and finally, to calculate the maximum torsional stress, we divide just the thread torque by the polar moment of resistance, and we got on this case around like 207 megapascal just coming from the tightening of the bolt. So as I told you before, VDI like told us we have just to take into consideration the two stresses, not just the stresses coming from the preload, like divided by the stress area, but we have to take also into consideration the stress coming from the tightening, which is in our case 207 megapascal. Now, since the bolt is like simultaneously like stretched and twisted, so we should combine both stresses using the von Mises equivalent stress equation recommended like by VDI 2230, which is, as you can see on this formula, it's like the root of like the stress max, which is coming from the excess from preload. Of course, not just this like stress, also in case we have in our model also like external load, so we should like have like extra stress in addition to this value. Actually, this will be like power 2 plus 3 times the parameter K multiplied by the tau max, which is the torsional stress we got like before, power 2. This factor is not more than a reduction factor, which is like used according to VDI, and it's like around 0.5. So this formula it's already prepared in this table, and if you apply it like actually by using this stress, which is axial stress from the preload and the torsional stress from both two these stresses, we come to the finalist equivalent stress, which is like around 595 or 96 megapascal. This is without external load. This is just the preload plus the stresses coming from the tightening, so we have to expect around 600 or 595 megapascal. So as you can see, the equivalent stress is already like very high, even before we apply the external 20 kilonewton load, as in our case here in our like bolt plate connection. And this explains like why simply looking at the ANSYS bolt stresses can be like misleading actually. So those results represent only the stresses caused by the external load, not the stresses like introduced during assembly. So to know the real stress state of the bolt, both effects must be considered. So in this video, we have calculated the assembly stress according to VDI 2230 by determining the preload, the axial stress, the torsional stress, and finally the equivalent stress during tightening. So this is the first part of a complete bolt verification procedure. But here is the interesting question. Now that we know the stress caused by tightening, what happens when we add the 20 kilonewton external load from our ANSYS model? Do we simply add the stress together? Actually, no. So according to VDI 2230, only part of the external load is transferred into the bolt actually, and while the remaining part is absorbed by the clamp plate. In the next video we will calculate the total stress acting on each bolt, determine the load distribution, and finally check whether our 4M8 bolts like the 8.8 Franks class can safely carry the applied load with an adequate safety factor against yielding. So as you can see in our or on this video, we got a stress of 595 megapascal, and we still expect to have an additional stress coming from the load that we have, which is 20 kilonewton distributed on these 4 bolts. But for more details, I will explain that in the next video. So if you don't want to miss that calculation, make sure to subscribe, and I will see you in the next video.